Let us now talk about conditional probability. In conditioning probability, we are limiting our sample space. We go from a sample space of E to E asterisk. The sample space has been reduced. Now let's not overthink this. I'm going to give you some formulas in a minute that make it a little confusing, but they work. Here's what we're doing. If I have boys and girls in some school somewhere, and we're talking about how many are left-handed and how many are right-handed, I can ask, well, how many are left-handed? Of course, it's 47 out of 150 is the probability of being left-handed. What's the probability of being right-handed? 103 out of 150. That's not conditional probability. If I limit the sample space, I say, of the boys, I'm just looking at the boys now, this becomes my sample space. Of the boys, what's the probability of being left-handed? It's going to be 15 out of 50, which is different from our 47 out of 150. Or if I say of the left-handers, well, if I say of the left-handers, then we're talking about this sample space. How many, what's the probability of being a girl, given that you're left-handed? Well, then our sample space becomes all left-handers, and the probability of being a girl, given that we're talking about lefties, is 32 out of 47. When we take conditional probability, the key is we are limiting the sample space. We're reducing the sample space. Here we have our official statement. The conditional probability of event A happening, given that event B is a precursor event, it's already happened, is found using probability of event A given event B is equal to probability of A intersection with B divided by the probability of B. Notice, whatever is in this second position is always your denominator. And of course, with any kind of rational fraction here, rational function, probability of B cannot equal 0 because it's in the denominator. If we have 0 in the denominator, we can't make sense of it. The second condition, the given condition, goes on the bottom. What are the implications of this? Well, of course, if we have probability of A given B is probability of A intersection B divided by probability of B, we can solve for probability of A intersection B. If I multiply both sides by the probability of B, I'll get probability of A intersection B is probability of A given B times the probability of B. It's important to know this one so you can manipulate it and get this one. Here we can solve for the intersection of A and B. Here's a fairly straightforward example using conditional probability. It says two number cubes are rolled onto a table. Find the probability that the sum of the number cubes is 5, given that the sum is less than or equal to 7. We know that probability of A given B is equal to probability of A intersection with B divided by probability of B. That's what we're working from. Well, if we want to know the probability the sum is equal to 5, given that the sum is less than or equal to 7, we can write it like this. Probability of sum is equal to 5, given that the sum is less than or equal to 7, which translates into the probability the sum is equal to 5, intersection, and the sum is less than or equal to 7, divided by the sum is less than or equal to 7. So we have to find the probability the sum is equal to 5. Well, we have 1, 2, 3, 4 situations where the sum is equal to 5. 4 situations where the sum is equal to 5, that's going to be automatically and less than or equal to 7. So 4 out of our 36 possibilities are less than or are equal to 5 and also less than or equal to 7. Divided by, well, what is the probability the sum is less than or equal to 7? It's all of these ones here. How many are there? There's 21 out of 36. When I multiply 4 over 36 by, I can multiply by the reciprocal, and I'll get 4 over 36 times 36 over 21. Those will cancel. I get 4 out of 21. And that is the correct answer to this conditional probability problem. You could have also thought, without using this formula here, you could also said, all right, I'm limiting my sample space to the sum is less than or equal to 7. So I make a circle here, and then I say, well, how many are equal to 5? Well, 1, 2, 3, 4 out of 21 are equal, satisfy these conditions, which is the same answer we got using our formula. Let's talk now about independence. We said that the events A and B are statistically independent if the probability of event B occurring is not influenced by the probability of event A occurring. Two events are independent if and only if the probability of event A given B is equal to the probability of A, or and also the probability of event B given event A is equal to the probability of of B. Here, probability of A given B is probability of A. It doesn't matter if B occurs or not. The probability of A will remain the probability of A. And here, it doesn't matter if event A, it doesn't matter what the outcome of event A is. Probability of B given A is the same as the probability of B. You have to know what this means here. For example, let's take we often say that the rule of thumb is if two events are physically independent, they are most likely going to be statistically independent. For example, if I flip a coin heads or tails and then I pick a card, 1 out of 52 out of a deck, the card is not influenced by the head or tail outcome. They are independent. The probability of getting a head given a king is still the probability of getting a head. The probability of getting a king, given that you flip the head, is the probability of getting a king. It doesn't change based on the outcome of the other part of the experiment. Perhaps a more convenient definition of independence is A and B are independent events if and only if the probability of A and B is equal to the probability of A times the probability of B. Before we saw they're independent if the probability of A given B is equal to the probability of A, and probability of B given A is equal to the probability of B. So we see this is a third way to look at independence. If the probability of A intersection with B is the probability of A times the probability of B, then they're independent. If they're independent if this is true and this is true as well. So we've got two separate ways to look at independence. At this point, I think it's important to just review the difference between mutually exclusive and independent events. For mutually exclusive events, A and B have nothing in common. It's one or the other. There's no overlap. Our Venn diagram looks like this, with A, the subsets A and B in our sample space U having no intersection. So the probability of A or B is equal to the probability of A plus the probability of B. Independent events means that the outcome of A will not influence the outcome of B, and vice versa. The outcome of B will not influence the outcome of A. Here's a rule of thumb. Physically independent leads to statistically independent. So the probability of A given B is simply the probability of A. The probability of B given A is simply the probability of B. Or you can think of it as the probability of A and B is equal to the probability of A times the probability of B. This is often used to test for independence. This is our last subject we're going to talk about with probability. It's called the law of total probability, also known as Bayes' theorem, which says the probability of event A occurring is the probability of B times the probability of A given B plus the probability of B times the probability of A given the complement of B. I'm sorry, the probability of the complement of B there too. Well, yes, you could try to memorize that, or you can think it through. Here I've done a tree diagram with event B occurring and then event A occurring. See, we've got event B occurring here and the complement of B occurring here. We know that those have to add up to 1. So let's say that this is 30% chance, or 0.3 of B occurring, so this would be 0.7 of B not occurring. And event A, or of course this would be the complement of A given B, this branch is also has to add up to 1.0. So let's say that this is 0.6, this would make this 0.4. I just made this up and I made this up. If we go with the complement of B, we have A, not A, or the complement of A given the complement of B down here. Well, if I'm looking at A, say this is 0.5, this would also be 0.5 here. Again, I made up this number, I made up this number, I made up this number because I know that each branch has to equal 1. I got this for free, and this for free. Well, let's see what it's saying. What's the probability of A occurring? We have A occurring here and A occurring here. Well, I have to multiply the probability of B, 0.3, times the probability of A given B. Well, this here is the probability of A given B. It's just that branch times 0.6. Plus, I'm going to add to that the probability of the complement of B, which is 0.7, times the other branch, which is also going to result in an A, which is 0.5. So ultimately, I went up with 0.18 plus 0.35, which is 0.53. I've got a 53% chance, or a 0.53 probability of getting A. Don't overthink that. You don't have to memorize this. You just have to know how to use the branches. Multiply the branch, add them together.